Hi, I'm Rich Hickey. I'm here to talk about Clojure, which is a programming language I wrote for the JVM. This particular talk is oriented towards people who program in Java or C# or C++. In particular, that I'm not going to presume any knowledge of Lisp. So you might find some of it tedious, although I am preparing for a talk I'm going to give at eCoop to the European Lisp workshop, where I'm going to talk about the ways Clojure is a different Lisp. So maybe some of this will be interesting to you in that respect. But that's the nature of this talk. It's going to be an introduction to the language, a flyby tour of some of the features. I'll drill down into some of the others. I started to ask this question before, but I'll just ask it again to sort of see, is there anyone here who knows or uses any flavor of Lisp, Common Lisp, Scheme, or Clojure? Okay, so mostly no. I presume a lot of Java or anything in that family, C++, C#, Scala, anyone? You must be playing with it, right? How about functional programming languages like ML or Haskell, the strict guys? Anyone a little? Don't really want to raise their hands about that one. Okay, that's good. In particular, I think coming from that background, you'll understand a lot of this straight away. How about dynamic programming languages? Python, Ruby, or Groovy? Yes, about half. And I asked before, Clojure, we have a few people with their toes in the water. The other key aspect of Clojure that would matter to you if you're a Java programmer is whether or not you do any real multi-threaded programming in Java or in any language. Yes? So some. So you use locks and all of that nightmare stuff. I'm a practitioner. I programmed in C and C++ and Java and C# and Common Lisp and Python and JavaScript and a bunch of languages over the years. Way back, this same group, I think it's the same lineage, was the CSIG. And when I first started to come, I started to teach C++ to the CSIG, and it became the C++ and CSIG, and eventually the C++ and Java SIG, and now the Java SIG. So back in the 90s, early 90s and mid 90s, I taught C++ and advanced C++ to this group and ran study groups, and I've come back tonight to apologize for having done that to you and to try to set you off on a better track. So we're going to look at the fundamentals of Clojure, and it will be also of Lisp in many ways. But I'm going to say Clojure. Don't take offense. All these things, or many of the things I say, are true of Clojure, or true of many Lisps. I didn't invent them. They're not unique to Clojure. But some things are. Then we'll look at the syntax and evaluation model. This is the stuff that will seem most unusual to you if you've come from a compile, link, run language and one of the curly brace C derivees like Java. Then we'll look at some aspects of Clojure, sequences in particular, and the Java integration, which I imagine will be interesting. And I'll finally end up talking about concurrency, why Clojure has some of the features it does, and how they address the problems of writing concurrent programs that run on the new and indefinitely, for the indefinite future, multi-core machines. And I'll take some questions. At some point in the middle, we'll probably take a break. I don't know exactly where that's going to go. So what's the fundamentals of Clojure? Clojure is a dynamic programming language. And dynamic has a lot of different meanings. In particular, it's dynamically typed. That would be an expectation you'd have of Python or Ruby or Groovy. It achieves that dynamic nature by being a Lisp. And I'll talk more about that. I don't see a lot of people who know Lisp here. But that doesn't mean there isn't a bias against Lisp. How many people have seen Lisp and said, oh my God, ugh, I can't believe the parentheses. And I would say I'd hope you'd put that bias aside for the purposes of this talk. It ends up that for people who have not used Lisp, those biases are have no basis. And for most people who have given it a solid try, they vanish. And in fact, many of the things that you consider to be problems with Lisp are features down the line. But having said that, Clojure is a very different Lisp. It's syntactically much leaner than a lot of Lisps. It has fewer parentheses. It uses more data structures in its syntax, and as a result, I think is more succinct and more readable. So maybe the time to try Lisp again. Another aspect of Clojure is that it's a functional programming language. And again, I'm going to talk in detail about these things. For now, you can just say that means a focus on immutability in your programs, to write programs primarily with immutable data structures. And if you're coming from another Lisp, this will be an area where Clojure is definitely different. I made different decisions about the data structures in Clojure. The third leg of Clojure, it sort of stands on 4 points. It's dynamic, it's functional, it's hosted on the JVM, and it embraces the JVM, its host platform. There are ports of other languages that sort of just sit on the JVM. There are ports of, for instance, Common Lisp that sit on the JVM. But they don't really connect very well for a number of reasons. One is they're implementing a standard. The standard was written before Java was written, and there's just no merging the type systems. On the other hand, Clojure was written for the JVM, and so it's very heavily integrated with it. So not only does it reside there, which is a benefit because you can run it if that's your environment, but it embraces it, which means the integration is good, and it's pretty transparent to go back and forth. The fourth aspect of Clojure is the concurrency aspect. I work in C# with guys writing broadcast automation systems. They're multi-threaded. They have all kinds of nasty stuff going on, multiple connections to sockets, lots of databases, data feeds from all kinds of places, and it's not fun writing programs like that need to share data structures amongst threads and to have them get maintained over time and have everybody remember what the locking model is. It's extremely challenging. Anyone who's done any extensive multi-threaded programming with the locking model knows how hard it is to get that right. So Clojure is an effort on my part to solve those problems in an automatic way with language support. And the last thing is, it is an open source language, and it's very transparent. The implementation and everything else is up there for you to see. We started to talk about this before. Why use a dynamic language? Some people are very happy. Of the people who are programming in Java, how many are happy about that? They like Java. They have no complaints. Okay, not too many. It ends up that I think many Java programmers look at people who are using Python or Ruby and being very productive, and I think justifiably envy their productivity, the succinctness, the flexibility they have, and in particular how quickly they can get things done. And it ends up that is a fact of the static languages, especially the ones like Java, that they're inherently slower because of the amount of well, some people call it ceremony that you have to go through to communicate with the language. It slows you down. So flexibility is a key thing you would look for in a dynamic language. Interactivity is another key point. Again, this goes back to Lisp. Lisp has pretty much always been an interactive language. And that means a lot of things. In particular, it means that when you've got a Lisp up and running, you feel like you are engaged with an environment as opposed to shoveling your text through a compiler phase to produce something else out the other end. So that interactivity is kind of a deep thing. The REPL is part of it. That means read, eval, print loop, and I'll talk about that in detail in a little bit. Dynamic languages tend to be more concise. That doesn't mean that static languages can't be. Haskell in particular is very concise. But the curly brace languages are not concise. Java is probably a great example of a language that's not concise. And that's just not a matter of tedium. It's a matter of where is your logic? How far apart is your logic? How spread out is it? Can you see what you're thinking about, or is it in pieces? Is it spread out by a bunch of things that are not about your problem? dynamic languages are definitely more suitable for exploration. There's a certain aspect in which static languages are like concrete. That's a good aspect when you're trying to finish. In some systems, concrete is going to be more resilient. It's more resilient to change. It's more structured and it's rigid. On the other hand, that's not necessarily the kind of materials you want to be working with when you're trying to figure out what your structure should look like in the first place. So dynamic languages are better for exploration. And in particular, what I like about dynamic languages and Lisp fundamentally, and I think in a way other languages don't achieve, is it lets you focus on your problem. You can, with Lisp and its ability to do syntactic abstraction, suck everything out of the way except the problem. And for me, when I discovered Lisp, I was pretty expert C++ programmer. I said to myself, what have I been doing with my life? It was that big a deal. So there are many dynamic languages. I'm going to talk about Clojure, and I won't do bashing of other languages, but I will try to highlight why you might choose Clojure over some of the other options, because in particular now I think it's a great thing that there are many dynamic languages available for the JVM, and dynamic languages are supported as a concept in the Java community. At Java 1 there was plenty of presentations on Jython and JRuby and Groovy and these other languages. And Sun has hired some of the developers of these languages and given it kind of official support as something that's viable to do on the JVM. So you're going to see mixed language programming being accepted in Java shops. So how do you pick? I think you can categorize languages in one dimension pretty straightforward. Are they a port of a language that exists somewhere else, or were they written for the JVM? Ports have a bunch of challenges. One is there is a canonic version out there, because most of these languages are not defined by a specification. They're defined by a canonic implementation. So there's CRuby, right? There's CPython. Those are really the languages. And the other things are ports, which have to struggle to follow along with the C version. The other problem ports have is a lot of the infrastructure for the languages, especially the ones that don't perform very well, are written in C. In other words, to get the library performance they need, the support libraries for Python are written in C. So an effort to port Python to Java means having to replicate those C libraries. So there's that. I would say the main appeal to a ported language is if you already have an investment in Ruby or Python, or you happen to really love the language designs, that's a good way to go here. I would say if not, if you're just starting from scratch, you may find that a language that's native to the JVM is going to give you better integration. The version you're using is the canonic version. The canonic version of Groovy is the JVM language. The canonic version of Clojure is a JVM language. And I would say of the two, Groovy is going to let you do what you do in Java, except a little bit more easily. Fewer semicolons, more dynamic. There are some builders, there are some idioms, there are closures. Sort of the fun of dynamic programming and a lot of the similar syntax to Java. So I think if you're just interested in dynamic and want to continue to write programs that are like your Java programs, Groovy can't be touched. Clojure is not about writing programs like your Java programs. Clojure is about realizing what's wrong with your Java programs and doing something different. And so you'll find some of that through the talk. So Clojure itself, it inherits from Lisp an expressivity and elegance I think is unmatched. Depending on your mindset, you may or may not agree, but there's a certain mathematical purity to lambda calculus in the way it's realized in Lisp. The uniformity of the syntax is elegant. Clojure also has very good performance. Again, I'm not going to get involved in any language bashing, but I'm pretty confident no other dynamic language on the JVM approaches the performance of Clojure in any area, and is unlikely to. But everybody's working on performance.
Can I interrupt just for a second?
Certainly.
If anybody here your Fox program. I'm not sure because they were sending something called.
We've converted them.
No,
They're Java programmers now.
only Java.
So the performance is good. I made a point before starting the talk that the objective of Clojure is to be useful in every area in which Java is useful, that you can tackle the same kind of problems. I don't write web apps and put stuff in and take it out of the database kind of applications. I write scheduling systems, broadcast automation systems, election projection systems, machine listening systems, audio analysis systems, and I write them in languages like C# and Java and C++, and Clojure can be used for those kinds of problems. Doesn't mean they can't also be used for web apps, and people did that right away with Clojure and database and UI stuff. But it has that same kind of reach. I mean, one of the nice things about Java is it has a wide range. Clojure has direct wrapper-free access to Java. Some of the ported languages have to use wrappers because those languages have their own object systems that imply a bunch of dynamic features that they have to glom on top of Java objects when you interoperate with them. Clojure was designed to provide direct access to Java. It looks like Clojure, but it's direct. Clojure, being a Lisp, is extensible in a deep way, and we'll talk a little bit more about how you get syntactic extensibility through macros. And then Clojure, I think, is completely unique amongst the languages on the JVM in promoting immutability and concurrency, much more so than even Scala, which is often talked about as a functional language, but isn't deeply immutable. It sort of is an option. Clojure is really oriented towards writing concurrent programs. And immutability for its other benefits outside of concurrency. So how does Clojure get to be these things? It is a Lisp. Again, put what you think about Lisp aside. I'll explain what that means in depth as I go into each of these points, but Lisp in general is dynamic. Okay, in that way, interacting with an environment, having a REPL, having sort of introspection capabilities on the environment, being able to modify things in a running program, are all characteristics that make it dynamic. A fundamental feature of all Lisps, if they want to be a Lisp, is that code is represented as data. And again, I'll explain that in detail. There is a reader, which is part of the implementation of code as data, sort of something in between your text and the evaluator. Being a Lisp means having an extremely small core. You'll find when you contrast Clojure to other languages, even languages that are theoretically lightweight like Python or Ruby, Clojure has way less syntax than those languages, far less complexity, in spite of the fact that they appear easy. Lisps generally have tended to emphasize lists. Clojure is not exactly the same way. It's an area where Clojure differs from Lisp in that it frees the abstraction of first and rest from a data structure, the concells, and in doing so offers the power of Lisp to many more data structures than most Lisps do. So there's that sequence thing, and I'll talk more about that in detail. And syntactic abstraction. Again, we have abstraction capabilities with functions or methods in most languages. Lisps take that to the next level by allowing you to suck even more repetition out of your programs when that repetition can't be sucked out by making a function. Okay, so we'll dig down a little bit more. What does it mean to do dynamic development? It means that there's going to be something called a REPL, a read, eval, print loop, in which you can type things and press enter and see what happens. I guess we should probably do that. So this is a little editor. It's kind of squashed in the screen resolution, but down below is the REPL. This is Clojure in an interactive mode, and we can go and we can say +1, 2, 3, and we get 6. We can do other things Java-like. I'll show you some more of that later. But the general idea is that you're going to be able to type expressions or in your editor say, please evaluate this. I mean, I can go up here to math.py and hit the keystroke that says evaluate this, and you see below we get that. And that's kind of what it feels like to develop. I'm going to show you even more after I explain what you're looking at, because I don't want this talk to be yet another where people are shown Lisp and not having had explained to them what they're looking at. So we're going to do that first. But you have this interactive environment. You can define functions on the fly. You can fix functions on the fly. You can have a running program and fix a bug in a running program. And that's not like being in a mode in a debugger where you have this special capability to reload something. It's always present. If you build an application with some access to the ability to load code, either a remote REPL connection or some way to do that, your running production systems will have this capability to have fixes loaded into running programs. In general, there isn't the same distinction between compile time and runtime. Compiling happens all the time. Every time you load code, every time you evaluate an expression, compilation occurs. So that notion of phases of compilation is something you have to relax when you're looking at a language like Clojure. And I'll show you the evaluation model in a second. I talked a little bit about the introspection, but that's present. You're sitting at a REPL. Clojure is there. Clojure has namespaces. You can get a list of them. Clojure has symbols. You can get a list of those. You can look inside the infrastructure that underlies the runtime and manipulate it. And that's what I mean by an interactive environment. I just don't mean typing things in. I mean, there is a program behind your program. That is the runtime of Clojure. And that's accessible. If I say something you don't understand, you can ask for clarification. I'm endeavoring to try to come up with the ideal way to explain Lisp to people who have never seen it. And this is what I've come up with, which is to talk about data. Lots of languages have syntax. You could talk about Java. You could talk about here's main and here's what public means and static, and then you could dig into arguments to a function and things like that. But we're going to start here with data, in particular data literals, and I think everybody understands data literals from languages they're familiar with. You type in, 1, 2, 3, 4, and you know that's going to mean 1,234 to your program. So Clojure has integers. They have arbitrary precision. They can get, as large as your memory can support. And the promotion of small integers to larger integers while arithmetic is going on is automatic. It supports doubles as the floating point format. Those are doubles. Those are big D double Java doubles when you type them in.
Traditionally simple tokens.
They're right. Right, they're Java doubles, but they're the big D doubles. Right, so one of the things you're going to see about Clojure is everything is an object. Okay, all numbers are boxed, at least until you get inside a loop where I can unbox them. But it's a language in which numbers are boxed. Unlike common Lisp, where you have access under the hood to use tagged integers and tagged numbers, which is more efficient than allocating them on the heap. No capability of doing that in the JVM. There's been talk about it, them adding it, which is stunning to me. Apparently there's this guy, John Rose, at Sun, who really does understand Lisp very well and has talked about all kinds of really neat features, which if they make it into the JVM would make it stunning, like tail call elimination and tagged numbers. But in the absence of that, numbers are boxed so that everything can be an object and can be treated uniformly. You have big decimal literals. You have ratios. 22 over 7 is something. It's not divide 22 by 7. It's a number. It's a number that's not going to lose any information versus dividing 22 by 7 and either truncating or converting into a floating point format where you will lose information. So ratios are first class. String literals are in double quotes. They are Java strings. Same thing, immutable, no conversions, no mapping. Being a native JVM language means I can just adopt the semantics of Java literals. I don't have to take strings from a language spec that said, for instance, they could be mutable, and have to force that on the JVM by having my own type and conversions to and from. So because I'm an immutability-oriented language, I'm very happy with Java's definition of a string being an immutable thing. So Clojure strings are Java strings.
Question.
Yes?
Is there any way to represent underlying units? In other words, to say that it's double 1.234, but unless you know it's centimeters, meters, something like that, you don't know.
No, try Frink. Have you ever seen it?
No.
Oh, you will love it. You can add all kinds of units and figure out how many, balloons of, hydrogen it would take to move a camel across this much distance. It's amazing. Units for absolutely everything. Old ancient Egyptian unit, it's fantastic. The guy is just a fanatic about precision, making sure you don't lose anything, but you can arbitrarily multiply all kinds of units. Everything is preserved. Everything works correctly. Fantastic. Frink. Frink. F-R-I-N-K. But no.
And is that Java or is that Lisp?
Frink?
Yes.
Frink is a language for the JVM. It's its own language. But it's a lot of fun. I've seen the guy talk, and he has some great examples. Some involve how many belches it would take to, move a hot air balloon to the moon and things like that. Okay, so we have string literals and double quotes. We have characters that are preceded by a slash, backslash. So that's a character literal, and that's a big C character, Java character. Now we're going to get to two things that are possibly a little bit different because they're not first-class things in Java. One would be symbols, which are identifiers. They can't contain any spaces. They have no adornments. Symbols are used as identifiers primarily in code, but they can be used for other things as well. They're first-class objects like strings. If you have one of these things, you can look at it, and it will be a symbol, Clojure Lang symbol. Fred and Ethel are two symbols, that's correct. The other thing Clojure has are keywords, which are very similar to symbols, except they always designate themselves. So they're not subject to evaluation or mapping to values by the compiler, like symbols are. So symbol might be something you would use for a variable. You could make Fred be equivalent to 5. You could never make colon Fred be equal to 5. Colon Fred will always mean itself. So when it gets evaluated, the value of the keyword Fred is the keyword Fred. It's sort of an identity thing. And they're extremely useful. They're very useful in particular as keys and maps because they're very fast for comparison and they print as themselves and read as themselves. That will make a little bit more sense in a minute. There are Booleans. This is different from Lisp, although there is still null is false, nil is false. But in addition, there are proper true and false, mostly for the purposes of interoperability. It ends up that you can't solve the nil becoming false problem. At least I couldn't. So there are true and false, and they're for use in interoperability with Java. You can use them in your Clojure programs as well. But conditional evaluation in Clojure looks for two things. It looks for false or nil, which is the next thing I'm going to talk about. Nil means nothing. It also is the same thing in Clojure as Java null. Didn't have to be, but it is. So you can rely on that. So nil means nothing, and it's the same value as Java null. So when you get back nulls from Java, they're going to say nil. Nil is traditional Lisp word. But I like it because also traditionally in Lisp, if you can say if nil, and that means it'll evaluate to the else branch because nil is false. Nil is not true. So that's another literal thing, that nil. There are some other things. There are regex literals. So if the reader reads that, it's just a string regex, exactly the same syntax as Java's, preceded by hash, will turn into a compiled pattern. So at read time, you can get compiled patterns, which you can then incorporate in macros and things like that, which is very powerful. and shows how that delineation between compilation and runtime is a little bit fungible.
So nil is different from empty list.
Correct. And there's a good reason for that. And the reason is empty list is no longer as special as it was once you have empty vector and empty map. However, the sequencing primitives, the functions that manipulate sequences, return nil when they're done, not the empty list. So that aspect of being able to test for the end of iteration with if is still there. So Clojure sits in a unique point. He's asking about aspects of Clojure that differ a little bit from Common Lisp and Scheme. There's like a long-standing fight between what should the difference between false, nil, and the empty list be. Should they be unified? They are in Common Lisp. Should there be some differences? There are some differences in Scheme. Clojure actually does some of both. There is false. However, nil is still testable in a conditional. It does not unify nil and the empty list, which is a difference from Common Lisp. However, all of the sequencing or list operations, when they're done, return nil, not the empty list, which is an important thing for Common Lisp-like idioms, where you want to keep going until it says false, as opposed to having to test for empty explicitly, which you would have to do in Scheme. Does anybody know Scheme here? Yeah, you know Scheme, but you know both, so you know what I'm talking about. For everyone else, I wouldn't worry too much about that because you wouldn't have presumed nil would have been the empty list, right? Probably not. Okay, so those are the atomic things. They can't be divided, right? That's what atomic means. Right? You can't, a number isn't a composite thing. But there are composite or aggregate data structures in Clojure, and they're kind of the core abstractions of computer science. Right? One is the list. And in this case, I mean very specifically the singly linked list. And even more specifically, the singly linked list in which things get added at the front. So when you add to a list, you're adding at the front. The list is a chain of things, which means that finding the nth element is a linear time cost. Right? It's going to take n steps to do that. On the other hand, taking stuff on and off the front is constant time, right? Because that's the nature of a singly linked list. So it has all the promises, all the performance promises of a singly linked list with stuff at the front. And its literal representation is stuff inside parentheses separated by spaces. There's no need for commas. You'll see some commas. Commas are white space in Clojure. They're completely ignored. You can put them in if it makes you feel better or makes things somewhat more readable, but they're not actually syntax. They're not considered by the evaluator. So any questions about lists? Stuff in parens?
Two parts. One, then obviously the comments up there are just for people. They're not part of the language. They're not needed there.
Right, well these commas, the ones between 1, 2, 3, 4, 5 and Fred Ethel Lucy are actually English commas. But there are some commas, for instance, when we get down to maps here, you'll see commas inside the data structure. Those are ignored. Those are white space.
I understand that white space in lists. What about the difference between comma and decimal in a number?
I don't support any commas inside numbers. The printed representations of numbers in Clojure are those of Java. In Lisp? No, in Lisp they grow at the front. What cons A onto something makes A the first thing in that list. And that's true of Clojure too. Yes?
Is it based on util?
Absolutely not. All of these data structures are unique to Clojure. I'm only giving you some very high-level descriptions of their representation and their performance characteristics, but what we're going to find out later is all of these things, and that in particular I'm talking about adding to lists. All of these data structures are immutable, and they're persistent, which is another characteristic I will explain a little bit later. So these are very different beasts, and they have excellent performance, yet they're immutable, and it's sort of the secret sauce of Clojure. Without these, you can't do what I do in the language.
In the second list, Fred, Ethel, Lucy,
Yes.
that list is, I don't want to use the words fixed, so you add to it, and you see a list coming out.
That's correct.
Fred, what Fred references, though, can you change?
Again, how this gets interpreted, we're going to talk about in a little bit. Right now, what you're looking at is a list of 3 symbols. You may end up within your program a data structure that's a list of 3 symbols. You may pass this to the evaluator and say, evaluate this, in which case it's going to try to evaluate each of those symbols and find out its value, and treat the first one as if it was a function. But we're not there yet. So that is a list of 3 symbols. The list at the end is a list of 1 symbol and 3 numbers. Heterogeneous collections are supported in all cases. I didn't necessarily show them everywhere, but they are. It's not a list of something. It's a list. It can contain anything and any mix of things. Okay with lists? The next thing is a vector. It uses square brackets. That should imply, I would hope, for Java programmers and people from that domain, array, right? Square brackets mean arrays. Well, they do now. So a vector is like an array. In particular, it supports efficient indexed access. Okay, it's an expectation you would have of a vector you wouldn't have of a linked list. That getting at the 50th guy is fast. It's not going to be 50 steps to do that. And the Clojure vectors meet that performance expectation. Fast indexing. In addition, it's a little bit like Java util vector or array list in that it supports growing, and in this case, at the end. And that also is efficient as your expectation would be of array list, as a constant time operation to put things at the end. Similarly, it can hold anything. The first is a vector of 5 numbers, the second is a vector of 3 symbols.
Must it be homogeneous?
No, all the collections can be heterogeneous. Okay, so far? So that's going to behave like an array in terms of being able to find the nth element quickly. And finally, as a core data structure, we have maps. Okay, and a map is like, well, it's like a Java map or any kind of associative data structure in providing a relationship between a key and a value. Each key occurring only once and having a mapping to a value. So the way they're represented is in curly braces. And they're represented simply as key, value, key, value, key, value. Again, the commas don't matter. So they're white space. They get eliminated. For instance, in the second map you see there, that's a map of the number 1 to the string Ethel and the number 2 to the string Fred. You don't need the commas. And the expectation with the map is that it provide fast access to the value at a particular key. There are usually 2 kinds of maps you would encounter in ordinary programming languages. One would be sorted, right? Some sort of sorted map, in which case the access is going to be typically log n, right, to find a particular guy, depending on how many things are in the map, because they use trees or red-black trees and things like that. And Clojure does have sorted maps. The one you get from the literal representation like this is a hash map. And the expectation of a hash map is constant or near constant time lookup of values at keys. And that maps to hash tables. So what you have in the Clojure literal maps is the equivalent of a hash table. It's fast. Everybody okay so far?
What happens if I introduce another key in this?
Another key,
A.
it will be replaced. Do you want it?
So the last one replaces the first one.
Correct. There are only one instance of a key in a map. Is that your question?
Yeah.
Yes. So if you were to say the function that...
No, I'm saying if I type it out like this.
Yes?
Put the comma, and after C3
It's probably a replacement. I see, in the same thing, yeah. I don't think it's an error. That's a good question. I might type it in later for you. Okay.
No one's so dumb as to have done that yet. I agree with you.
Yeah, I mean,
for the set, it's kind of a similar question.
it's the same thing. Yeah, it's the same thing. Well, but there's no associated value, so Fred will be there. So let's talk about sets. The fourth thing I'm showing you here is sets. Sets are a set of unique values. Each value occurs only once in the set, and really the only thing the set can do for you is tell you whether or not something's in it. There's no associated value. It's just, does the set contain this key? Do you have a question?
Yes. Does it keep it the same? Does it, as it is added to the set, does it keep it in the sorted order?
There are sorted sets and hash sets. Same thing as with the maps. The sets here are hash sets. So no, the order is not retained. You can request a sorted set and the order will be the sort order. Does that answer your question? Okay. What is the test for equality? Equal. The equal sign is the test for equality, and equality means the same thing for everything in Clojure. It means equal value. You'll see that Clojure definitely de-emphasizes identity, and completely. In fact, there is an identity function, and I have yet to use it. Clojure is about values. Identical contents are identical by equals. That's made faster than you might imagine by caching hash values. But equality is equality of value in Clojure.
And there's immutability.
Immutability helps, certainly. Well, it's, if you've ever read Henry Baker's paper on egal, Clojure implements egal, finally. If you haven't, and don't worry about it. So yes, equality is equality of value. All right? Yes? Hi, Rob.
If you were going to Java library code and using the actual Java code, you wouldn't use it?
No, you can make arrays and you can interact with Java arrays that are arrays of either objects or native arrays. You can say float array and the size and you'll get an array of floats. So you have the ability to do Java stuff. I'm going to emphasize the Clojure data structures because they let you do what Clojure lets you do. You can access Java, but if you start accessing mutable things, some of the things Clojure can do for you, we can't do. Doesn't mean you're not allowed to do them. But there's no point in me showing you how to interact with the Java array, except to show you the syntax, which I might later. So the last point about this is that everything nests. A key in a map can be another map. It can be a vector. Anything can be a key or a value. Because of this equality semantics, there's no problem having a vector or a map whose keys are vectors. That's perfectly fine. So if you needed to use tuples as keys, pairs of things as keys, that's just completely doable.
Question in
Yes.
terms of performance. Underneath, it's again a hash because it's immutable that makes the key and therefore it's still lose.
Well, you can get the hash of a vector.
I mean, as a programmer task to invoke it, but rather at an implementation level.
At an
Implementation level to say that you can have a very complex structure with
Mhm.
the key.
Correct.
Some value.
Right.
That sounds expensive to me, unless
Well, it depends on what you're doing. I would imagine that really complex structures are not frequently used as keys, but they could be. Can that be helped? Yes. The fact that these are hashed by default means that once and once only, the hash value of some aggregate structure will be calculated, and that will be cached. So there's a quick hash test. Otherwise, we do the deep value check. But again, I don't think you're going to encounter complex data structures as hash values that often. But using kind of small things like tuples or other small maps as keys is tremendously useful. It's really, really handy to not even have to think about that. I think we got one other Clojure programmer arrived who can possibly attest, independent of me, how Clojure's performance is. How's Clojure's performance?
Fine for me.
Yeah.
Especially on the recent tests that have been showing up on the list.
Right. Well, now there's some extra numeric goodness in there. But these data structures are pretty good. What's the reality? The reality of these data structures is I've tried to keep them all within 1 to 4 times a Java data structure. The equivalent Java data structure. In other words, hash map, vector. Well, singular linked lists are pretty straightforward. So they're within striking distance. The B side is, in a concurrent program, there is no locking necessary for use with these data structures. If you want to make an incremental change to a data structure in a certain context, there's no copying required to do that. So some of these other costs that would be very high with a mutable data structure vanish. So you have to be very careful in looking at that. The other thing that's astounding to me, at least, is that the lookup time, again, the add times are higher than hash map, but the lookup times can be much better because this has better cache locality than a big array for a hash table. Okay, we're all good on this? I probably have to move a little bit quicker. Yes, more quickly.
Yeah, when we get a complex data structure, can you decompose it?
There is destructuring, yes. I actually won't get to talk about that today, but there is destructuring. There is not pattern matching, okay, but there is destructuring to arbitrary depth of all of these. Destructuring means a way to easily say, I want to make this set of symbols that I express in a similar data structure map to corresponding parts of a complex data structure on past. Clojure has that. It has some really neat destructuring capabilities. All right, so what's the syntax of Clojure? We just did it. I'm not going to talk about semicolons, curly braces, when you have to say this, when you have to have a new line, or anything else. Because the structure of a Clojure program is a data structure or a series of data structures. There is no other stuff. There are no rules about where things go. There are no precedence rules. There's nothing else. You write a Clojure program by writing the data structures I just showed you. That's it.
Which means, how does one do an if?
I'll show you. So you write a program by writing data structures. The data structures are the code. That has huge implications. It is the nature of Lisp. There's a fancy name for it called Homoiconicity, and it means that the representation of the program is done in the core data structures of the program, which means that programs are amenable to processing by other programs because they're data structures. So I'm not going to talk any more about text-based syntax because there is no more. Now many people claim of Lisp, well, Lisp has no syntax. And that's not really true. It doesn't have all this little fiddly character syntax necessarily. There is syntax to the interpretation of the data structures. We're going to see a lot of lists. They have different things at the front. The thing at the front will tell you the meaning of the rest. All right, so let's talk a little bit about evaluations. So how does this all work? We should all know from Java or many other languages like Java. Okay, we types our program into a text file, and we save it. And then we send those characters of that text to the compiler, who has a very involved, abstract syntax tree and parser and lexer that interpret the rules of the language. This is what constitutes a character. This is what constitutes a number. And then furthermore, if you've said if and you put parens and then you said some stuff and you put a semicolon and you happen to have put else, then you're still in this construct called if, things like that. It knows all about that, and it deals with the text. And it will tell you if you've met the requirements in terms of it being a valid program, and then it will turn it into something that can run. In the case of Java, that something will be bytecode, and it will go into a class file or a jar file. We know this, right? And then there's a separate step, which is called running, where we take that stored executable representation and we ask it to happen. Usually, in this case, we'll say, Java dash something class file, and it will run. And it will run, and then it will end, and it will be over. And we could try again if we didn't like it. That's the traditional edit, compile, run, be disappointed, start over.
Well, that's only true for development. In production, anything can run for days.
Oh, correct. But I'm talking about the development process. Right? Yeah. Yes. The runtime is just that part.
Hopefully in real code, that's the main event.
Until you realize it's not working, and you have to ask everybody to please wait for our downage while we fix it. Right? That's the difference. Yeah, if you read about Erlang, which is getting a lot of press, they'll tell you about phone switches and how that's really not allowed. And Lisp was doing this for a very long time, this kind of live hot swapping of code and running systems. I think it goes more, in this case, it's less about the production thing than it is about what's the nature of developing your program. Because as a developer, seeing it run and saying, ooh, that was bad. I wonder what happened. I wish I had run it in debug mode. I wish I had put a breakpoint somewhere interesting. And I'm really sad that I spent an hour calculating that data and dropped it on the floor because I have to do it again with the breakpoint in. That's a lot different experience than keeping your program around and having that data stay loaded and fixing your function and running it again without starting over. So that's what happens in Clojure. You take the code, text, could be, characters. There is character representation, and what you showed there can be represented in characters in ASCII. It does not go first to the evaluator. It goes to something called the reader. And this is the core part of what makes something a Lisp, which is that the reader has a very simple job. Its job is to take the description I just told you. Keyword starts with a colon, and a list is in parentheses, and a map is in curly braces, and it's pairs of stuff. Its job is to take those characters and turn it into data structures. The data structures I described. You start with the paren, you say stuff, you close the paren, that's going to become a list when the reader's done with it. You start with square brackets, that's going to become a vector when the reader's done with it. So what comes out of the reader are data structures. And what's unique about a Lisp and Clojure is that the compiler compiles data structures. It does not compile text. It never sees text. What the compiler gets handed is maybe a list with 3 symbols in it, or a vector with 5 numbers in it. That's actually what the compiler has. It has a data structure in hand with actual data in it, not text. And it compiles it, and in the case of Clojure, it is a compiler. There are many, well, there are actually many Lisps that are interpreters, but many people believe that Lisp is interpreted. And it's certainly easy to make an interpreter for Lisp that would take those data structures and, on the fly, produce the values they imply. But Clojure is a compiler, and in particular, Clojure compiles those data structures to Java bytecode right away. There is no interpretation in Clojure. So it's a compiler. It produces bytecode just like Java C does. And because it's an interactive environment, it presents that bytecode right away to the JVM to execute. And it executes right away, and you can see the effect. Yes?
Are they living in the same VM as the application's running?
When you're in the REPL, you have a VM, right? You have one thing. So yes, your environment is your program. Your compiler is in your program. Yes?
So they're all circumstances, like say the final product include?
Yeah, I mean, some commercial lists give you tools to take out the compiler in production, mostly because they don't want you giving away their compiler. Normally, there's no reason to prevent that because it's a useful thing to have, particularly when you want to load code later to fix problems. You're going to need that compiler there. So in Clojure, there's no strip out the compiler option.
Right, so then it's like, I guess it's all written in Java, right? So
We'll see that there is a core of Clojure. The data structures are written in Java. The special operators are written in Java. And then most of the rest of Clojure is written in Clojure.
right, but okay, so no native code.
There's no native code. Clojure is completely a pure Java project. Right, there's no native code, there's no C libraries, there's nothing. It's all Java. either generated by Java itself or generated by Clojure. It does not turn off the verifier or anything like that in order to get performances. There have been some schemes that tried to do that. Clojure is completely legit that way. So when we have this separation of concerns between the reader and the evaluator, we get a couple of things. One of the things we get is we don't have to get the text from a file, right? We can get it right from you. You just saw me type right into the REPL an expression. Never went through a file, never got stored. So the first thing you get is this kind of interactivity of you can just type in stuff and say go. That's a big deal. I mean, if you've been programming in Java or C++ long enough to remember when the debuggers didn't give you the ability to evaluate expressions at a breakpoint, you remember how hard that was. You always have that capability here, to have expressions directly evaluated. What else do we get from this? Well, we get the ability to skip the characters completely. For instance, it's quite possible to write a program that generates the data structures that the compiler wants to see and have it send them to the compiler to be evaluated. So generating programs are a common thing in this kind of an environment. Whereas this kind of stuff, when you're doing it with text, is really messy.
By the way, one observation this chart may actually give a good way to be able to say it. There are firms I know that because of compliance requirements that they have, they might be very comfortable with code producing stuff going into a reader or a program, a fixed program that produces stuff.
Mm-hmm.
But it's that option of saying it's always live, a person in this production environment can influence the code that's being executed. That's the scary part.
Well, I mean, that's a security policy thing, whether or not you expose this in a production system. So I'm talking about you could, if you needed to, you could have that over a secure socket channel and have it be just an administrator who knows what they're doing, have that capability. Because the alternative is downing your system. If you don't have that, and of course opening this in a production system, that's completely a policy thing. It has nothing to do with the language. Except if your language doesn't let you do it, you can't do it.
That's fair.
So it does. The other thing is that these data structures, you might write this program and have this happen directly. Then you might say, I like this program. Let me take those data structures in this thing called the printer, which will turn them back into that, which you could store and somebody could sign off on and say, this is the canonic program, which our program generated, that we're going to use. And we'll lock that down and do whatever. Yes?
So are the data structures physical files? Or
No, they're in-memory data structures. The ones your program would see. So, an instance of Clojure lang persistent vector might get handed to the compiler. The compiler's got to deal with it, figure it out. So there's one more thing that this allows, and this is the secret sauce of all Lisps, including Clojure, which is what would happen. I mean, it's fine to sit standalone and write a program that generates a program. But what would happen if we said, you know what, we're handing these data structures to the compiler, right? It would be great if the compiler would let us participate in this. If it could send us the data structures, and we could write a little program, a very small program, and give it back different data structures, then we could participate very easily in the extension of our language. Because this compiler, it's going to know how to do what it knows how to do. It's going to know what to do with the vector. It's going to know what if means and a couple of other things. But there'll be new things that we'll think of that we'd love to be able to say. Right? When you have something you'd love to be able to say in Java, what do you have to do? You have to beg Sun and wait for years and hope other people beg for the same things, and you get it. That's it. You have no say. You have no ability to shape the language. In Lisp, that's completely not what it's about. It's about getting you in the loop. And in fact, the language itself has a well-defined way for you to say, this is a little program I'd like you to run. When you encounter this name, I don't want you to evaluate it right away. I'd like you to send me that data structure. I know what to do with it. I'm going to give you back a different data structure, and you evaluate that. That's called a macro. And it is what gives Lisp and Clojure syntactic abstraction and syntactic extensibility.
Can that happen in the context of a namespace?
Yes, it can. There are namespaces in Clojure, and they allow me to have my cool function and you to have your cool function.
By the same name.
Cool function, yes. So that's what makes Lisp amazing. It's something that I won't have time to dig deeply into tonight. If you can come away with at least the understanding that that's how it works, that's how it's possible, and the fact that these are data structures here and here makes it easy. You could theoretically say, oh, I could write something, and if the compiler could hand me the abstract syntax tree, I could navigate it with some custom API and do whatever. It's not nearly the same, though, when what the compiler is handing you are those 3 data structures I just showed you that every program knows how to manipulate and has a wildly huge library that directly can manipulate. So that's how Lisp works. I'm going to try to speed it up a little bit. In Clojure, unlike Java, everything is an expression. So you know in Java there's a difference between declarations and statements and expressions. There's no distinction in Clojure. Everything is an expression. Everything has a value. Everything gets evaluated and produces a value. Sometimes that value is nil, not particularly meaningful, but everything is an expression. So the job of the compiler is to look at the data structures and evaluate them. There's a really simple rule for that. It's slightly oversimplified, but in general you can understand it this way. All those data literals I showed you, right? Symbols, numbers, character literals, vectors, maps, sets, are all evaluated by the compiler to represent themselves, except lists and symbols. Lists and symbols by default are treated specially by the evaluator. So when it reads a list of symbols in particular, it's going to do some work. It's not just going to return the list of symbols to your program. It's going to try to understand them as an operation, which I'll show you in a second. So symbols, the compiler is going to try to map to values, okay, like variables. Like in a variable, you can say int I equals 5. Later in your program in Java, you say I. Java is going to try to figure out, oh, that's 5. That's the I you set up there. Same thing in Clojure. When you use a symbol in your data structure, Clojure is going to try to find a value that's been associated with that symbol. It can be associated with it through a construct called let, which is sort of the way you create a local name, or through def, which is the way you create a global name. Or it's a list, and it's going to say, this is an operation of some sort. I have to figure out what to do with a list. So how does that work? Well, again, we said, what's the data structure? It's parens. It starts with something. It may have more stuff or not. But from the evaluator's standpoint, all that matters is the first thing. The first thing is the operator, or op. That's going to determine what to do. And it can be one of 3 things. It can be a special op. Okay? This is magic. This is sort of this is the stuff that's built into the compiler upon which everything else is bootstrapped. So some things are special. I'm going to enumerate them in a second. It can be a macro, like we saw before. There's a way to register with the compiler to say, when you see the op, my cool thing, go over here and run this function, which is going to give you something to use in place of the my cool thing call. And the third thing it could be is an ordinary expression. It's going to use the normal means of evaluating an expression, and it's going to say whatever value that yields, I'm going to treat as a function and attempt to call with the calling mechanism of Clojure, which is not limited to functions, but you can its main purpose is for functions. So for people who know Lisps, Clojure is a Lisp 1. It is a Lisp 1 that supports def macro well, and the use of namespaces and the way backquote works makes that possible, and everyone else can ignore that.
Before you step away, that last bullet point, an expression which yields a function as opposed to it's the function.
Well, what it's going to encounter is it's going to encounter a list, and the first thing is going to be the symbol Fred. Fred is not a special operator. No Fred in Clojure. Let's say no one has registered a macro called Fred. Then it's going to use the rules we said before about symbols to find the value of Fred, where hopefully someone before has said, Fred is this function.
Or something that at the end yields a function.
It won't keep evaluating. It's going to evaluate that expression.
That's what
But there are other function-like things or callable things in Clojure in addition to functions. I'll show you that in a second. So let's dig down into each of these three pieces. Yes?
If it doesn't encounter any one of those three,
You have an error at runtime. It'll say, it's not a function. Effectively, what will happen is it will say, this is not a function. If you said, Fred is def Fred 1, so Fred is the number 1, and you've tried to call Fred or use Fred as an operator, it's going to say 1 is not a function. Probably with a not very illuminating stack trace. Okay, so special operators. There are very few. I think one of the things that's really cool about Lisp, and it's also cool about Clojure, is you can define most of them in terms of themselves. One of the great, brilliant things that John McCarthy did when he invented Lisp was figure out that with only, I think, 7 primitives, you could define the evaluator for those 7 primitives and everything you could build on them, like the core of computation. It still gives me goosebumps when I say that. It is a beautiful thing. It really is. And if you've never looked at the lambda calculus or at Lisp from that perspective, it's quite stunning. His early papers are just great, and they're just brilliant in a transparent way. So let's look at a couple. I'm going to show you 2, and then I'm going to list the rest. Def would be one. How do we establish a value for a name? There's a special operator called def. It takes a name. Now, that name is going to be a symbol. Obviously, that can't be evaluated, right? Because the whole purpose of this special operator is to give it a value. If the compiler were to use normal evaluation of the name position, you'd have a problem because you're trying to define what it means. How could you do that? So one of the things about special operators that you have to remember, and it's true of macros as well, is they can have non-normal evaluation of their arguments. Like, the arguments might not be evaluated. In fact, def doesn't evaluate the name. It uses it as a symbol, and it associates that symbol with the value. It does not evaluate the symbol. So this is a simple way to say, if I say def name some expression, the expression will be evaluated. The name will be mapped to that value or bound to that value. When you later go and say name, you'll get the value it was used to initialize it.
You mean you do that once?
You actually can do that more than once. You shouldn't do that more than once unless you're trying to fix something. In other words, def should not be used as set. But you can use def to define a function, and later you can use it again to fix it. So the things that are defined by def are mutable at the root, and it's probably, it's the only escape hatch for that dynamic change in Clojure. That's not governed by transactions or some other mechanism. Okay, so it establishes a global variable. Again, there are namespaces. I don't have enough time to talk about them, but it's all subject to a namespace. If you're in a namespace and you define the name, then it's in your namespace. It's distinct from that same name in another namespace. Namespaces are not the same as packages in Common Lisp. They're very much different. In particular, symbols are not inherently in a namespace. Symbols have no value cell. They're not places. They're just labels. And there are vars, which are the places, more like Common Lisp symbols. If is another thing that's built in. And if you think about if in your language, which you may not have ever done, right? If you thought about if as, why couldn't if be a function? Why can I say if some test expression, some then expression, some else expression? Why can't if be a function? I mean, it looks like a function. Well, it doesn't actually look like a function in Java, but why can't it be a function?
Evaluating truth or not.
Excuse me?
It's evaluating truth or not truth.
Well, it's either way.
It should only evaluate one of these two.
So
that's why, right? And a function evaluates what? All of its arguments. So if you tried to write if as a function, you would have a problem because functions evaluate all their arguments. So if has to be special, and if is special in Clojure too. It evaluates the test expression. And then, depending on the truth or falsity of this in kind of a generic sense, for Clojure, this is nil or false, it will evaluate that. If it's anything else, it will evaluate this. But it will only evaluate one of those two things.
It must have an else clause?
No, it doesn't have to. The else can be missing, in which case it defaults to nil. So if is another example of something that has to be special. It can't evaluate all of its arguments. Then we have these others. In fact, this is it. Right? There's something that defines a function. Something that establishes names in a local scope. A pair of things that allow you to do functional looping, to create a loop in your program. Something that lets you create a block of statements, the last of which will be the value. Something that allocates a new Java thing. Access to members of Java things. Throw, try, do what you expect from Java. Set will rebind a value. And quote and var are kind of special purpose for Lisp manipulation things, so I'm not going to get into them tonight. Question?
Is that the entire list?
Yeah.
So then what's the equivalent of that?
Of def macro? Def macro is bootstrapped on this.
So there's no keyboard, no...
Oh no, there is def macro, and it's defined a couple of pages into the boot script for Clojure, which I might show you if we have some time. Yes?
I'm just intrigued. The reason for the exclamation point on the set is it trying to say something to the program?
Yeah, this is bad. What are you doing this for? Yes?
I thought that factor would have to be a special operator.
No, it ends up that in Clojure, macros are functions. And so there's just a way, to, on the var, say this function is a macro, and it will be treated as a macro instead of as a function. Okay, so that's a tiny set of things. In fact, when you take out the stuff related to Java, it's an extremely tiny set. I don't think I made it down to 7. 1, 2, 3, 4, 5, 6, 7, 8. I have more than McCarthy's 7, but I don't have dozens. So how could this possibly work? This is not enough to program with this. No. No. So we need macros. Okay. There are plenty supplied with Clojure. And what's beautiful about Clojure and Lisp is you have the same power that I have to write macros. When you see the kinds of things that are implemented in Clojure as macros, you realize the kind of power you have as a developer because you can write those same macros. You could have written them. You don't have to wait for me. I'm not Sun. This is not Java. You want to do something, you have something you want to express a certain way, you want to extend the language that way. If you can do it with a macro, you can do it without contacting me or asking me for the favor of adding a feature for you. Which means the language is much more extensible by programmers. So let's look a little bit about how they work. If we remember, we're getting data structures passed to the compiler. So it looked at the first thing, and somehow there's a way, and I can't show you that tonight, to say this name designates a macro. And associated with that name then is a function. The function expects to be passed the rest of the stuff that's in the parentheses. So we had this cool function, my cool macro. Maybe it expects to be passed 2 things. The things it gets passed are not evaluated. It gets past the data structures that the compiler got passed. Because the compiler is going to say, you told me you know how to do this. Here are the data structures. Give me back the data structure I should be processing. So it's a transformation process where the macro is handed the data that's inside the parens as arguments to the function that the macro is. It will run any arbitrary program you want to convert that data structure into a different data structure. You can write macros that look stuff up in databases, that go and ask a rule-based system for advice. Most are not that complicated. But the thing is, it's an arbitrary program transformation. There's not a pattern language. There's not a set of rules about this can be turned into that. It's an arbitrary program, a macro. And in this way, it's like a common Lisp macro that, given the data structure, gives back its own replacement. Replace me, the expression that began with me, with this. And then keep going, which may yield another macro and another round of that, or it may yield something it already knows how to process. Yes?
So would it be correct to say that in Clojure macros have a runtime cost?
No, this is happening at compile time. This is part of compilation, right? The compiler got handed this data structure. It said, oh, it begins with the macro name. Hands it to the macro, it comes back. That transformation occurs, it keeps compiling. Then you get bytecode. After you get bytecode, there's no more talking to the macro. So macros replace themselves with another data structure, and then compilation continues. So we can look at a macro. You'll notice on the list of primitives, there's no OR. OR is not primitive in Clojure. And in fact, if you think about OR is not primitive. OR is not a primitive logical operation. You can build OR on top of if. Right? The OR I'm talking about is like the double bar OR in Java, in that what happens? If the first part tests true, what happens to the second part? Not evaluated, right? It's still got that magic thing, but if already knows how to do that. If already knows how to do a conditional evaluation of only one of two choices, which means we can define OR in terms of if. And so this is what happens. So OR is a macro. When it's expanded by the compiler, it returns something like this. So I'm going to say OR X or Y. And this is what comes back, another data structure. It begins with let, which we haven't seen so far, but let says it takes a set of pairs of things. It says make this name mean this inside the scope of the let. It's like a local variable, except it's not variable. You can't vary it. But it has the same kind of scope. So it says, let's do that. And the reason why it does it is because this is going to be some expression. Right? It looks like X here, but it could be like a call to calculate some incredibly difficult thing that's going to take an hour. In which case, I probably wouldn't want to repeat that more than once in my expansion, because it would calculate that thing twice. So we're going to take whatever that expression is, put it here, assign its value to this variable name, which is made up. Because obviously, you wouldn't pick this name. It's a good machine pick name. So it makes a variable, and then it says, if that thing is true, right? We took an hour to calculate this, right? We have the value. If that's true, return it. If, right, we know, is it going to do this? If this is true. Otherwise, it's going to do what? And that's the implementation of OR. If the first thing is true, it returns it. Well, in fact, in Java, you don't get a good value, but in Clojure, you get the value that was true.
Then the invocation of any function can both return a value in a true-false, or you interpret certain kinds of values.
All values can be placed in a conditional, not just Booleans, and it's subject to the rules I said before. If it is nil, or if it is false, you'll get the else expression evaluated. If it is anything else, 7, the string Fred, anything else is true. So Clojure, like most Lisps, allows any expression to be evaluated as the conditional test. Here.
I'm sorry, there's also then the part that there are no side effects of evaluating X. In other words, I'm struggling.
No, I talked about that. Let's say this X took an hour. Right? A well-written macro will make sure it only gets evaluated once. I could have put if X, X, Y, yes? No, this is the answer to your question. I could have said if X, X, otherwise Y.
Correct.
Then if X had side effects, it would happen twice. Then we make this a not well-written macro. This is a well-written macro where it needs to use that expression twice, which means it's going to bind a temporary value, a temporary variable to the value, which means X only happens and appears only once here. So if it had a side effect, it would happen only once. If it took a long time, it would take a long time only once.
Simple as it is, I still have a
let appears to take 3 arguments. So,
Let actually takes, at the topmost level, it takes n arguments. The first of which has to be a vector of pairs of things. You can have multiple expressions. Name, value, name, value, name, value in a let.
That or on this one, this 158 is one symbol.
This is one symbol, yeah. Is that clear? Yeah. So, and then let is a block, so it actually can have multiple expressions in it. In this case, it has only one.
and then it just does whatever's next.
It returns the value of, well, this is a macro, and all it's going to do is give the compiler back this, and the compiler has to keep going with this in hand now.
Yes. I'm just trying to figure out what let
Let establishes this name to be this value.
Yeah.
Then, when let runs, the series of expressions inside let run, and the last of them is the value of the let expression. In this case, there's only one expression inside the let. In this case, there's only one expression inside the let, so the value of the if expression is the value of the let, which is what we want because we want this to mean or.
And that's the scope. Right.
This is the end of the scope over here. This paren matches that one.
That's what I was noticing. So I was.
Yes, and well, it's one of the beautiful things about this system, which we'll see clarified in a moment, is that all expressions are bound. So we don't have a lot of complexity with precedents and terminators and things like that. It started with the paren, it ends with the matching paren later.
What about the big boolean in the
Big Boolean?
Yeah, Java big boolean.
In fact, it has to be big Boolean false. If it's coming from Java, I test to make sure because an improperly constructed big Boolean may not be Boolean.false. New Boolean is wrong. And in fact, not only is new Boolean wrong, but the reflection API in Java uses it exactly that way. So it returns multiple different values of big Boolean false.
I got it. It's not working.
I have a patch that looks for that because I got bit by that already. So it will make conversions of big Boolean falses that aren't Boolean.false into Boolean.false. I'm sorry, I didn't write Java, I only wrote Clojure. But the point here is that this seems like a primitive thing. Like if the language doesn't have it, you're in trouble. It is not. If I had somehow left out or, you could have added it. You could have written the macro that does this job and added or to Clojure. I'm sure I forgot some things in Clojure. You could add them. Many things. In fact, we saw how tiny the special operators list is. And, or, cond, all kinds of things are built on top of these things as macros and or functions. And after the point of the special ops, you can't add a special operator, but you can add a macro.
Okay, so now I got more of like a 50,000 foot question. So I mean, I get this. This is great. So somebody builds a bunch of macros, and then somebody uses that as a palette to build another bunch of macros. And
Right.
somebody else has got this like smoking domain-specific language.
Right.
Somebody is what it comes out to be, and it's 3 or 4 developers in, and 3 or 4 levels in.
Right.
There's a runtime error, and I get a stack trace. What do I get?
You're going to get a reference to the expansion, the inside of the expansion.
The bytecode has got everything expanded. It's flat.
Correct.
So how do I figure out where in my source corresponds to what went wrong?
That can be challenging.
That was the answer I was expecting. Wasn't the answer I was talking about. I guess
It's still an area.
people will be busy for a long time, which is great. That's cool. So,
I think that one of the things that's good about Lisp is because you have the ability to work in the small and to say, I just wrote this little component of this thing. I'm going to run this right now. I don't have to wait till the big program that contains this runs. Your ability to do that immediate unit test to make sure that thing is working is good. On the 50,000 foot level, propagating up from macros, the source of the problem in the macro, is something that's being worked on. Some compilers do it pretty well for Common Lisp. It's an area I hope to enhance in Clojure. But it will always be more challenging than a function. And that's why macro writing is not for newcomers or the inexperienced part of the team.
It seems akin to language design.
It is language design. It definitely is. On the other hand, without it, you're limited to the abstraction capabilities of functions, which are limited. Think about how much you repeat in Java. Think about how much code you repeat to close files in Java. Think about it. Think about how many times you've written the exact same thing. I mean, having your IDE spit it out is a little bit handier, but when you decide, oh, I need to change my policy about doing this, I want to check something else, all that generated code is not amenable to, to fixing. So those kinds of things that can't be, whose redundancy can't be eliminated by functions, can be eliminated by macros. And that's something you want to do, because the B side of this is, if you're doing all that stuff by hand, yes, it's transparent, you get this debugger error. Okay, you did that by hand. Where? All over your program, right? Because you didn't have a macro that generated it. You don't have one place to fix. You have n places to fix. So there's a...
You have n places to fix where you see, oh, I made this mistake everywhere, but it shows
But-
up in one place.
But you still have to find everywhere you have to fix it.
Yeah.
And these things are idioms. Everybody that programs in Java has to know this. These idioms are only by convention, and they have to be manually replicated.
There is a part, I mean, it has not taken over, but aspect-oriented programming somehow feeds into the solution.
It is an attempt to address those cross-cutting concerns, but it's still unproven as to whether or not people will describe those things in advance, because what tends to happen is that you don't know it, and then you say, oh, I'm doing this all over the place, and then will you implement an aspect? Is there a policy? Is there a way to describe an aspect that will insert it everywhere it's needed? That's a very challenging problem.
But the problem of discovery is a little bit easier with aspect-oriented.
I mean, I think aspect-oriented programming is interesting, but it's different. So anyway, there's a trade-off with macros. Yes, it may be less transparent there. On the other side, when you fix a macro, you fixed every usage of the macro. Finally, we get to the easier thing. I mean, I started with special operators and macros mostly because that's the evaluation order. But functions exist, and they're kind of straightforward. The first thing about functions you need to know is that they're first-class values. They're values like any other. Methods in Java are not first class. You can't put a method into a variable. You can't pass a method to a function. They're special things. In Lisps, and in fact in most dynamic languages today, functions are first class, which means the function is a value. So I've defined 5 to mean 5. And of course I don't need to do that, but I'm showing you a def, right, of a symbol to a value. Now I'm going to show you a def of a symbol, SQR, to a value, which is a call to one of the other special operators called fun. And what fun does is it creates a function object. This is going to turn that code into something that gets compiled into a function that takes one argument and multiplies it by itself. So,
For a second, any invocation of SQR will look to see it's being invoked with just one argument and say something's wrong.
it's a regular function. It's going to be an instance of a Java interface that takes an argument. It's a real regular method in the end in Java.
If something was being invoked with 2 arguments, it would say
You'll have an invalidarity problem. Okay, I need to move a little bit more quickly, so let's hold the functions for a little bit. Let me move forward. So this fun, I can't describe all of the features of fun. It's an exciting and rich thing. But the simple one that we can take as being fun is a special operator. It takes a vector of the names of its arguments. That's the simplest way of understanding it. And then it contains a set of expressions, which will be the body of the function. The last expression is the value returned by the function. There's no return statement in Clojure. So when we say square 5, it returns 25. Okay, this is a function call. Again, we said, what does it do? It says, is square a special operator? No. Is it a macro? We're going to say right now it isn't. So what's the value of square? It's this function object. Okay, call it and pass it that. The value of that. Okay, so the arguments to functions are evaluated. So it's going to pass square the number 5. Square is going to multiply by itself and return 25. So functions are first class. There are other things that are like functions. In other words, the compiler says, can I call this? The answer is true of funds. It's also true of other things. In particular, one of the neat things about Clojure is that maps are functions. Because if you think about maps mathematically, they are functions. Maps are functions of their keys. Given a key, a map should return the value of that key. And it does in Clojure. So maps are functions. Sets are also functions. Vectors are also functions. Vectors are functions of their indices. Okay? That's cool stuff. And when you see idiomatic Clojure, some of it is quite beautiful because of that relationship. So, we'll try to summarize this. Things that would be declarations or control structures or function calls or operators or whatever in Java, all are uniform in Clojure or any Lisp, in that there are lists where the operator is the first thing in the list. So we've reduced all of this variation here to something uniform. So we'll look at each one. Int I equals 5 establishes I as a name whose meaning is the value 5. Def I does that as well. But where in this does it say it's a definition? Whatever some rule about the shape of this thing says it's a definition. In Clojure, def says that's what it means. Okay? If x is equal to 0, return y, otherwise return z. When does this end? I haven't shown you the rest of the program. Is this done? Got me. You don't know, I don't know, right? Because it could say else, right? Else if, right? It has to say else if, and then it could say else, right? We have to keep looking forward. We could not have had an else, right? It's not closed. In addition, without these returns, it doesn't yield a value. This is a statement in Java, right? There is an if conditional, which is an expression. They're two different things. In Clojure, if gets first, we know what we're dealing with. If, it's here. We saw the syntax. It takes three things.
What's the question mark in 0, question mark in Clojure?
That's a function name.
Okay.
You can have question marks in names. Clojure is much more liberal about the symbols that can appear in names, but not completely liberal, because I need some symbols for myself. X times Y times Z, what are these? Mathematical operators, again, another special thing about Java. And they can go in between things, and there's precedence rules, all other kinds of gook, right? Clojure, what? It's the beginning. I don't have to look anywhere. I don't have to look in the middle or look for semicolons. What's happening? Multiplication first. Also, you'll notice multiplication can take multiple operands, more than 2. It's not just a binary operator. It's an n-ary operator. Foo x, y, z, this is what? Function call, right? Foo x, y, z. People complain about the parentheses list. How many parentheses difference? None, right? You move it from here over there. Same thing. Same thing. I don't know what you're talking about. And you're never going to see curly, 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 curly. Yes, you may see parens like that. But it's better, I'm telling you. It keeps your program near itself. You have to go down to the next page to see the next step. And then this member access, I'm going to talk more about the Java interoperability. But same kind of thing. Different number of parentheses? No. Different number of dots? No. But dot goes first because dot tells Clojure we're doing some Java stuff here. And that has its own special interpretation because dot is a special operator. We saw before. So there's a tremendous uniformity. There's a lot of value to that uniformity. I know a lot of programming languages, and every time I have to learn the arcane whatever the rules are, syntax, and this thing next to that means that, and this character means this, and you can have a semicolon here but not there, and it better be indented by the same amount, or whatever it is, I really get angry now because there is no reason for that. It is not better than this. And if you use this for any amount of time, you will not disagree because there's no one who does.
But it also has to have its idiosyncrasies in some ways. Foo.bar.who, paren x, in Java. How would that be expressed in Clojure?
I'll show you later. If I only have another hour, I have to go much faster. Everybody ready? So let's hold the questions until like a question time. Unless you're really confused, but just general interest things we'll hold. Because I may cover it. One of the things that is typical about Lisp is that it has a rich library for manipulating lists. But it ends up that, I think, in my opinion, it's a shortcoming of Lisps traditionally, that those functions are limited to a particular data structure, which is the singly linked list. Because the functions that underlie that abstraction are broader, and there are three of them. The first is, I'd like to obtain some sort of a sequence-like thing from some sort of a collection-like thing. That's an abstract way to say something. Given that sequence-like thing, I want and need only two functions. One is to say, give me the first thing. The other is to say, give me the sequence that is the rest of this sequence. In the case of seek, if there is no stuff, it returns nil, because nil means nothing. Which means you can say seek call, and you can put that in an if expression as a test thing, and because nil returns logical false, you'll know there's nothing to do. That's an important idiom of Common Lisp Clojure preserves, unlike scheme, where you have to say empty all the time. If it's not empty, you will get back an object. That object only makes two promises. You can call these two functions on it. Right? This function promises one thing. There will be a first element, because we already covered if there's not a first element here. So if you say first of the seek, and this is not null, it means you have a seek, you get back a guy. The first thing in the sequence. If you call, the second thing you can do with the seek is you can call rest on it, which says, give me the sequence that represents the rest, not including the first thing. Of course, if there's no more, what should we get? Nil. Right? Because we said here, nothing. If we have nothing, we get nil. Otherwise, we're going to get another seek. This is an extremely abstract way to talk about lists. But the advantage over Common Lisp and scheme lists is they would promise that the return value of this thing is a con cell. And that is a real limitation. Because now I can make seek work on absolutely everything. Seek works on lists because they have the structure. But it's possible to create a seek object. If you think about iterators, and I don't want to make this analogy extremely weakly, right? There's a way to walk through a vector, right? Similarly, there's a way to walk through a map. There's a way to walk through a string. There's a way to walk through a file. And it ends up that seek is supported on all those things. You can walk through Java arrays, all the Clojure collections, strings, files, everything. And you can use these two operations to move around. This abstraction of listness, and which I call a sequence because a list is more of a concrete thing, is bound to lists in most Lisps. Wow, this is hard to say. But is not in Clojure. And it's, I think, one advance of Clojure in the Lisp world. Which means that you can apply these things to everything. So what does this mean? Well, this is kind of primitive. I mean, walking through step by step. But what it means is that you can build a library on top of these primitives that provides a lot of power for manipulating data structures without loops. I'm just going to show you a tiny, tiny little bit. But it should give you a feel for what it's like to program in Clojure if you would think about what it would take to do these things in Java. For instance, I have a set of things. I'd like to have everything except the first two things. Right? We say drop 2 from whatever the collection is. That happens to be a vector. It could have been a list. It could have been a string. We drop the first 2 characters. Whatever it is, there's a way to abstract out the notion of walking through it. Drop means leave out that many and give me the rest as a sequence. Take is the opposite. It says only give me 9 of these things. But look at this second function, cycle. Cycle is a function call. It takes 1, 2, 3, 4 in this case. Could take any sequenceable thing. It returns an infinite list, an infinite sequence of those things around and around in a cycle. How could it do that? Isn't that going to chew up all the memory on my machine? Cycle? Sounds like a really scary function. It does that because if we go back to the definition of this, is there anything about the way I describe the operation of these things that says that the rest of this thing has to exist? I could make up the rest right when you ask me, right? And how much of it would I have to make up? Just one more thing. The thing I give you has to have one more thing in it, and I'm okay. And it could delay the calculation of the next part till the next time you call rest. That's called laziness. And in fact, all of the sequence stuff I'm showing you for Clojure is lazy, which means that you can write sequence functions that return infinite sets. And you can use them as long as you don't try to consume all of them. You can consume a little bit of them. So in this case, we're making an infinite sequence out of 1, 2, 3, 4, and we're taking the first 9 things from it. This looks like a weird abstract thing, but I've had plenty of programs in reality. I've had to do exactly this thing, round robin. You can use it to round robin work dispersal. You can use it to get distributions. I mean, cycle, it seems like some theoretical, isn't this cool, you can make an infinite sequence. But it really has utility. It ends up in real programs. And it goes on and on. Interleave does what you think. One from this sequence, one from that. Makes a new sequence. Again, one of these could be infinite. Right? You'd only make as much of this as you needed to match the length of the non-infinite one. Partition. Split this up into pieces. Think about the loops to do this stuff. And in Java, you have to write every one, every time. Right? Never mind the laziness part. Now we get to a more interesting function, which is map. Okay? Now we're not talking about map, the data structure. We're talking about map, a function, which is, again, from Lisp land, which says, take this function. Right? So the first argument of map is a function value. And apply it to pairwise, or however many sequences I give you, the elements of the sequences I provide. So in this case, we're going to call the function vector, and we're going to call it on A and 1. Then we're going to call it on B and 2, and C and 3, and D and 4, and E and 5. And vector makes vectors out of whatever you pass it. So we're mapping vector across this pair of sequences to vectorize corresponding elements of those sequences. We get a set of data structures back out of this. So map is a very powerful thing. Instead of saying for each blah, 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 do this and stick the answer into this collection, you say just map this function across this data. And it'll give you back a set of new data, the result of applying that function to each thing. You can also apply it against multiple sequences. That's what this is doing. Maybe I shouldn't have done something this complex here. Apply is also very interesting, and it's a unique thing to Lisps and languages that are dynamic. Apply says, I'm also going to pass you a function. And what I want you to do is take the next expression and figure out the sequence it yields, and then use that as the arguments to a call to this function. So we're going to apply the function stir, and stir says, given any set of things, turn it into a string. Turn each part into a string, and concatenate them all back together into a string. So we want to put that together, and what interpose does is it says, take this thing and put it in between everything in this sequence. So interpose, comma, ASDF is going to turn ASDF into a sequence and return characters. So we're going to have the character A and a comma, S and a comma, D and a comma, F and a comma. 7 things. Yes? 4 things with 3 things with 2. 7 things. And we say, apply stir to that, which means string concatenate them. As if they were the arguments to stir. In other words, if I called stir and said stir A comma, S comma, D comma, F comma, F, it would make a string out of them. Well, I can just apply it to this sequence as if I called it with those arguments, and it will do the job. I get back a single string with that in between. Again, if you don't quite get these, it's okay. I'm just trying to show you the power and the succinctness of this. Reduce is another function that takes a function. It says apply this function to successive pairs of the sequence you're given, taking the result of each application and using it as the first argument of the next. So if you say reduce with plus, you're going to get the first 2 things plus each other. And then take that and do that plus the next thing. And take that and do that plus the next thing. That's what reduce does. So this is effectively is summing this range. Range is a function that returns a sequence of numbers. And you can set where it starts and where it ends and how it steps and things like that. This is obviously a much higher level way to write programs than you do in Java. Yes? No? Or your head hurts. I don't know. What is it? Yeah, let's take a break. This would be a good time for a break. Does anybody have any questions on this real quick?
With cycle, what's the I guess I'm looking at the cycle between values and then calling take 2 arguments.
Right, and cycle returns a sequence which has only got 1 in it, and the recipe for producing the rest of the cycle. Sort of like a delayed function. That's what happens inside cycle. It doesn't produce an infinite list, obviously.
Okay, because
It returns an object that satisfies.
it returns a sequence.
It returns a sequence, correct.
Okay.
Go ahead.
Why can't you call stir directly?
Why can't you call stir directly? Well, in this case, I'd have to write A, comma, S, comma, D, comma, F, comma. Right?
You just call stir and then
It's then you're passing stir a sequence. And what I want to do is say, take that sequence and pretend it was the arguments to stir. Not an argument to stir, but n arguments to stir. Right?
Why slash comma and not quote comma?
Because that's the syntax of Clojure. Slash comma is a character literal for comma. Quote is used for other things. That's why I don't use it for character literals. All right, let's take a break.